Okay, this set of lecture notes is the introduction to lecture notes 10. This is chapter 9 in the book. It's about assessing studies that use multiple regression. So the last few lecture notes we've been looking at different functions with interaction terms between two different x variables, like the x and the z variable, for example, or nonlinear regressions, interactions of x with itself, or different functional forms for our regression model. Now we will talk about how to choose between different specifications, or how to look at what somebody else has done and evaluate it or pick it apart, sort of. So the question in this set of lecture notes is, how do we evaluate our own work and the statistical work of others? What are some criteria we can look for? So let's first define the population studied. It's the population of individuals, companies, etc., from which the sample of data was drawn. So we're going to have, if we're evaluating test scores and student-teacher ratios like we have been in the course, this is going to be, we will see in this set of lecture notes, California. It's the school districts in California. The population studied is the school districts in California. The other definition is the population of interest. This is the population we wish to draw inferences about. Okay, so if we want to find out the effect of class size on test scores across the entire United States, the question here is the population studied, California, a sufficient population to draw inferences about the entire U.S., or should we sample from school districts across the entire U.S. to draw inferences about the entire population of the U.S.? So this is just an example. The population studied here is California, and the population of interest is entire U.S. So the question is the population studied a reasonable sample to draw inferences about the entire United States? All right, another definition, internal validity. The definition of this is if the statistical inference about the causal effects are valid for the population being studied. What do I mean by statistical inference? I haven't really defined that. Statistical inference. Statistical inference is just the estimates of our beta parameters, and their standard errors, their statistical significance. If we find that beta 1 is positive, suggesting that class sizes increases in class sizes increase test scores, that our statistical inference would be that we should increase class sizes to increase test scores. Does that make any sense? For internal validity, we look for two things, two conditions. We look for the OLS estimators to be unbiased, or we want the OLS assumptions to be satisfied. We might think of this as the accuracy. We know that there's a population parameter out there, beta 1, and we want to make the argument that beta 1 hat, our estimate, is accurate. It's unbiased. The second condition is that the hypothesis tests that we specify should be rejected with a desired significance level. And we can think of this as maybe precision. So the first is accuracy, and the second is precision. Precision being that our standard errors are small enough that the estimates are meaningful, right? So if we estimate that class sizes, a reduction in class size increases test scores, but the standard errors are really large, and we can't reject our null hypothesis of zero effect with any meaningful confidence level, then we have to come to the conclusion that class sizes don't have a meaningful effect on test scores. So if we can only reject our null hypothesis with 50% confidence, that's not very high confidence. So for internal validity, if the statistical inference about the causal effects are valid for the population being studied, in other words, our population studied is California, we estimate a model using California data. Do the estimates apply to school districts in California? Do we believe our estimates for school districts in California? Not considering the entire U.S. right now, just thinking about the population studied. Do we believe the estimates for the population study? That's internal validity. And we want these two conditions to hold. We want our OLS assumptions to hold, and we want to estimate we want our model to be estimated with at least 95% confidence, rejecting these our hypotheses with at least 95% confidence. External validity, on the other hand, is if the inferences and conclusions can be generalized from the population and setting to other populations and settings. So this is asking the question, we've estimated our model on California data, now can we extrapolate the results to the entire US? Does it make sense that when we estimate a model on California data, the same effect size we can expect the same effect size in Massachusetts or in Mexico or in Germany? We have to ask ourselves that question. So that's external validity. Okay, so going forward, we are going to talk about threats to each of these. Threats to external validity and threats to internal validity. Threats to external validity first. So differences in populations. We might expect the causal effect to be different between the population studied and the population of interest. So if our population studies is California school districts in 2005, can we expect to find the same effect in Massachusetts in 2005? Maybe. California and Massachusetts might be fairly similar. Can we expect to find the same effect in Mexico in 2005? Okay, now we're getting a little bit to the point where we might not think that the effects in California are going to be the same as the effects in Mexico. So can you take your estimate of beta 1, let's suppose you estimate this model on California data, and then Mexico sees that you've done this and says, we want to hire you to analyze the impact of class size on test scores in Mexico. And you say to yourself, I could save myself a lot of money and just apply the beta 1 estimates from California to Mexico to get predicted effects on test scores in Mexico of reducing class sizes. But that's going to save you money, but that's not very practical. It's not likely that the effect of class sizes on test scores is going to be the same in California as it is in Mexico. So you probably should get data from Mexico and re-estimate your model. Going even further, how about Germany in 1946? Can we apply the results from California in 2005 to Germany in 1946? Probably not. There was a lot going on in Germany in 1946, World War II, for example, that's going to make Germany, the population in Germany a bit different. So more generally, what we're concerned about is that the population studied was chosen in a way that makes the characteristics of the people in the study unique. We might choose to study the effect of a drug on people that show up at a hospital. Those people are more likely to be sick in the first place because you don't go to a hospital if you're not sick. And so they're going to be different from the entire population of people in the United States or wherever we're studying. An extreme example, we might study the effect of a drug on mice or rats in a lab experiment. Can we extrapolate those results to humans? The population study is mice in a laboratory. Will the effects be the same on humans out in the population? Humans are doing a lot more than mice in a laboratory. So perhaps they're going to be different. Perhaps the effects are going to be different. And humans are different than mice. Another example, student test scores, student high school test scores we might not be able to extrapolate to college test scores. So the effect of class sizes on high school students might be different than the effect of class sizes on college students. Another problem is differences in settings. So that was differences in populations. Differences in settings is even if the populations might otherwise be the same, the setting can be different. So we might have college students in Colorado and Wyoming. Generally, college students in Colorado and Wyoming might look fairly similar. But there might be differences in the regulations between the two states. For example, an anti-drinking advertisement might have different impacts on college students in Colorado and Wyoming simply because the penalties are different, or an anti-marijuana use advertisement might have different impacts because the penalty for using marijuana in Wyoming is severe, while there is no penalty for using marijuana in Colorado, unless I guess you're under 21. So unfortunately, there's no statistical test for testing external validity, or testing whether or not we can extrapolate our results to other populations. This is all based on argument and knowledge of the populations. We can, however, if we have the ability, we can go and collect data in different populations. So we'll see that the book does this for California and Massachusetts, and they compare the estimates of the effect of class sizes on test scores in California to estimates of the effect of class size on test scores in Massachusetts. Without extra data, we just have to rely on argument. Okay, so that was threats to external validity. Now let's talk about threats to internal validity. Do the estimates apply to the population being studied? There's 5 major threats to internal validity, and if you go through each of these, if you think about how each of these might affect your estimates, then you can pretty much, if you can rule out all of these being a problem, then you can assume that your estimates are internally valid. The first is omitted variable bias. We've talked a lot about that one. The second is misspecification of the functional form of the regression function. What do I mean by that? That's just, should we have a nonlinear regression? Is the effect of x on y linear, or are there some important nonlinearities, like x squared or x cubed, log of x, etc.? That's lecture notes 7 and 8, I believe. The third is imprecise measurement of the independent variables, or we might call this measurement error or errors in variables. Number 4 is sample selection. And number 5 is simultaneous causality. And we'll go through all of these individually. So the bottom line is that all of these imply the OLS assumptions are violated, particularly the first assumption, the expectation of u conditional on x is equal to 0, meaning that something in the error term is correlated with the x variable. Okay, omitted variable bias solutions. If you have the data, include the omitted variables in the model. So pretty simple. If for example, in our test scores and student-teacher ratio example, we've been seeing that percent English learners is an important omitted variable. If we have that data, we simply include it in the model, and it solves the omitted variable bias problem from leaving that variable out. There's of course additional omitted variables that we might not have data on, so we need more complicated methods to deal with that. So the more complicated methods are something that you would learn in a graduate econometrics class, or maybe 435 if you go on. There are trade-offs to adding additional variables to the model. So the benefits of adding additional variables to the model is that they would reduce bias in our coefficients of interest. So they would reduce omitted variable bias by adding them to the model. There's costs. The costs are that the additional variables tend to reduce statistical significance of the existing coefficients. Not necessarily, but it might be the case that when we add additional variables to the model, we increase the variance of our beta estimates. So we might lose precision when we add variables to the model. How do we decide if we want to include a variable in the model? Well, we've looked at this before. The book shows us that we compare specifications. We look at the statistical significance of the coefficients that we've added to the model. We basically look at this trade-off that we just talked about. We look to see if adding the variable changes the coefficient of interest. So when we add %EL to the model, it causes the magnitude of the student-teacher ratio coefficient to decline, which indicated that %EL was an omitted variable that was causing bias. So that suggests that we should include it in the model. And then also we need to think hard about whether or not %EL actually, or our omitted variable actually makes sense to include in the model. Does it affect our dependent variable y, and is it correlated with our x variable? And then finally, when we add it to the model, is it statistically significant itself? Is the coefficient on the omitted variable, when it's added to the model, statistically significant, or can we reject a null hypothesis that the coefficient on the omitted variable is equal to 0 with 95% confidence? So basically the bottom line for this class, for solutions to omitted variable bias, is to add the omitted variables to the model and test whether or not they're statistically significant. Solutions to misspecification of the functional form. So see lecture note 8 on interactions and nonlinear regressions. So we're going to test different functional forms. We want to throw in x squared, x cubed, log x, and see if those models are better fits of the data than x entering linearly. So we saw F tests on different coefficients, or joint hypotheses about the statistical significance of multiple coefficients simultaneously. So we want to test those different models and see which one fits the data the best. Number 3, measurement error. So far we've assumed that x is measured correctly. This is often not the case. For example, there might be data entry errors. So if somebody is entering the data manually, maybe they're putting data into Excel, they might accidentally press an extra 0, or they might lose concentration and enter the data incorrectly. Recollection errors in surveys. So if somebody asks you what's your income, maybe you don't know exactly what your income is, or maybe you're going to lie because you don't want people to know what your income is. You're going to inflate your income. You might also lie on a survey if somebody asks you how often you drink and drive, or people might lie about that, or the survey might ask an ambiguous question. So this is all to say that X might not perfectly measure what we're trying to capture. So what does this look like mathematically? Suppose we have the model, the baseline model, y is a function of x, this model here, and this is the correct model. And xi is the unmeasured or true value of x. So this is what we wish we could measure, but we don't actually have this measurement. So xi is the true value of x for every individual. Maybe this is the true income. What we actually measure is x wiggle here. X wiggle. It's the observed or imprecisely measured value of x. Now x wiggle is equal to xi plus some additional error term, this bit here. Xi is equal to, or x wiggle I is equal to xi plus or in other words, the mismeasured value is equal to the true value plus some additional error term. So this error term is going to be our measurement error. Then a regression, if we plug this in, so we can rearrange and plug this into our regression function, then a regression is actually this, what I've just underlined. Y is a function of x wiggle minus the error, the measurement error plus UI. Now the important question is there correlation between the error term UI and the measurement error? Is there a correlation between these two things? If there is, then EI, the measurement error, is an omitted variable that's going to cause bias in our coefficient estimate for beta 1. So EI is just an omitted variable, and we've reduced this to an omitted variable bias problem. So the question we need to ask ourselves is the correlation between EI and UI equal to 0. If so, then EI, if it's not, actually this is I wrote this wrong. If the correlation is not equal to 0, then EI is an omitted variable, causing beta 1 to be biased. Actually, in all cases, it's going to be an omitted variable that's causing beta 1 to be biased. So if EI is correlated with UI, then it's the systematic measurement error, which is going to cause beta 1 to be biased in either upwards or downwards. If EI is uncorrelated with UI, then it's called classical measurement error. And so EI is purely random, and the correlation between EI and UI is equal to 0. With some algebra, we can show, this got erased, sigma squared x. So with some algebra, we can show that beta 1 converges. When there's classical measurement error, beta 1 converges, beta 1 hat converges to beta 1 multiplied by this term here that I'm circling or outlining in blue. It's the variance of x over the variance of x plus the variance of this measurement error term. So of course, if there's no measurement error, then the variance of the measurement error goes to 0, and we just get the variance of x over the variance of x. So beta 1 hat converges to beta 1, which is what we want. But when there is measurement error, then we know that beta 1 hat is inconsistent. It's converging to something, beta 1 times something. So what is that something? It converges to beta 1 times something. That something is this term here, the sigma squared x over the sigma squared x plus the sigma squared e. So this thing has to be less than 1 because, well, sigma squared x, all variances are positive because they're squared. So this is sigma squared x over sigma squared x plus something, so this has to be less than 1. So beta 1 hat will be biased downwards or towards 0. So this is called attenuation bias. This is classical measurement error. Classical measurement error, when the error or the measurement error is purely random and the correlation between the EI and the UI is equal to 0, we're still not out of the woods. Beta 1 hat converges, is inconsistent, and converges to beta 1 times something that's less than 1, so beta 1 hat will be biased towards 0. As a side note, if there's measurement error in Y, that does not cause attenuation bias, but it will increase the standard errors of our beta hat estimates. So measurement error in Y is still a problem, but it only affects our confidence levels, our precision of our estimates. So the solution is to check your data. So take a look at, plot the data, look at summary statistics, see if there are outliers. So look at your data and see if there's any measure that seems implausibly large or implausibly small. And then think hard about, should you remove that data point or should you leave it in the model? All right. Number 4, sample selection bias. This violates the independently and identically distributed assumption. So, for example, suppose we want to test the effect of a drug on the population. If we were random sampling, we would go out and randomly select individuals and randomly assign treatment to the randomly selected individuals. But it's more likely we seek participants for a study. So for doctors, and we want to figure out, does giving a drug to certain people increase their health or decrease the probability of dying from cancer or something like that? What we should do is we should go out and we should randomly select people and randomly give those randomly selected people some of this drug that we're testing. But what's more likely is that we don't have the ability to randomly select people from a population. Instead, what we're going to do is we're going to sit at our hospital, wait for people to show up, and then ask them if they want to participate in this study. So we need to ask ourselves, of course, who's the most likely to participate? Well, it's going to be people that are already sick, because people that aren't sick don't show up at a hospital. So we need to consider that giving this drug to people that are already sick might have different effects than giving a drug to people that are not sick. And it might be lower income people. It might be that people that show up to the hospital are lower income, or they already have underlying health problems. So we need to consider those things. So that would be sample selection bias. Another example is that we might be looking at a study that evaluates the effect of education on income. If you get an additional year of education, how does that affect your income? So in these studies, we often look at only the employed population, right? So we can't look at the income of people that are unemployed because they have zero income. So we're going to look at the effect of education on income for the employed. So this biases the coefficient upward because we're leaving out the college grads that are unemployed. Or it calls for a reinterpretation of the coefficients. So we could, this is solution number 1 to the selection bias problem. We reinterpret the coefficients. So in this case, we would reinterpret the coefficient to be the effect of education on income for the employed. Another solution would just be randomized controlled trials. So we could randomly assign education to different people and see how that affects their income. Or we could randomly assign drugs to different people in the population and see how that affects their health. Number 5, simultaneous causality. 2 main examples here. Well, first of all, what is simultaneous causality? Simultaneous causality is when we write down our model, we usually assume that X affects Y. So we're usually going to put the thing that we think is affecting the affecting variable on the right-hand side, the X side, and the thing that is affected, we're going to put that on the left side, the Y variable. But what happens if Y also affects X? So what happens if the causality goes both ways? There's 2 kind of classic examples of this. The first is demand and supply estimation. So if we write down a demand equation that looks like what I've written down here, quantity is a function of prices, we can write this down, and it looks, the way I've written it down implies that prices influence quantities. I've written prices on the right hand side, so the beta 1, we would think that beta 1 is capturing the effect of a change in price on quantity consumed. But what if the quantity consumed also affects the prices, the price of goods? So that might be the supply equation. So if you're a supplier, you might be setting your prices based on what people are purchasing, or the quantities people are purchasing. So it could be that the causality goes prices affecting quantities, but also quantities affecting prices. Another question we should ask ourselves is this a supply function or a demand function. Is beta 1 negative, meaning that this is a supply function or a demand function? Remember, in fact, in micro we put prices on the y-axis and quantities on the x-axis. So if it's a demand function, then beta 1 hat is less than 0. If it's a supply function, beta 1 hat is greater than 0. So which one is it? So in a graduate econometrics course, we would come up with solutions to identify which function we're estimating and how to get unbiased estimates of the coefficients. The second example of simultaneous causality is what we might call a peer effects regression, or how do my peers affect me? So in this case, I've written down a model that says that my test score of individual I in group J, is a function of the average test scores of my group J. So what this is saying is, if naively, if we just look at this regression, we might think that I'm estimating the effect of the average test score in my class on my test score. And that's what beta 1 would be picking up. But in reality, the average test score is influencing my test score, but I'm also influencing the average test score in my class. Or if we reduce this to just two people, suppose we are just two people in a class, and we're trying to figure out how, so there's two people, there's Bob and Mary in a class, and we can estimate this regression on both Bob and Mary's test scores. So if we did that, we'd have a data set with Bob's test score on the left-hand side and Mary's test score on the right-hand side in one row of the data, and then in the next row we would have Mary's test score on the left-hand side and Bob's test score on the right-hand side. So that would just be the influence of Bob on Mary and the influence of Mary on Bob. So which one is beta 1 picking up? The influence of Mary on Bob or the influence of Bob on Mary? In reality, it's picking up both, and we can't distinguish between which one is the most important. So the beta 1 estimates the influence of my peers on me and of me on my peers. So this is simultaneous causality. Solutions to simultaneity, again, randomized controlled trials. So we could randomly assign students to peer groups and see how those peer groups have influenced student outcomes. And then the other is take a graduate course in econometrics. We could teach more solutions to simultaneity. So next up, we're going to do we're going to evaluate two studies outlined in the book: the effect of class size on test scores in California relative to the effect of class size on test scores in Massachusetts.